You see, the conduction in metals is basically because of the free electrons available. These free electrons which have left their outermost orbit are also known as conduction electrons. Suppose the atomic weight of some metal is A naught. It means 1 gram atom, commonly, most popularly known as 1 mole. It will have the number of atoms equal to Avogadro's number, and the mass will be equal to atomic weight itself. Suppose we want to find the number of atoms per unit volume. Listen again. Number of atoms per unit volume, then you see volume can be given as mass upon density, and mass here is for 1 mole, it is A0 upon D. In place of volume, you can write A naught A0 upon D. You want to find the number of atoms per unit volume. This is N, and here you need volume. Volume for 1 mole could be given as A naught upon D, and this will go to numerator. That's what exactly I have written here. Number of atoms per unit volume, D is density, A naught is the atomic weight. You see, when we say that in a metal there are free electrons, what does it mean? From one atom, suppose one electron has been released or it has been detached, so it has left basically one positive ion behind it. That means if one electron is released from every atom, number of free electron and number of positive ions are equal. But the possibility is there that one atom releases 2 free electrons, then in that case number of positive ions that will be divalent will be 1. One positive ion having plus 2 charges will be responsible for 2 free electrons. That means you can't say that number of free electrons is always equal to the positive ions. Number of free electrons could be greater than number of positive ions. You see, free electrons which have been released, which have been detached from the atom itself, is now free to move all around. Because of the thermal energy, these electrons move very, very fast with the velocity that is of the order of 10 to the power 6 meter per second. This is known as random velocity, and this is very high, 10 to the power 6 meter per second. During their motion, they collide on and off with the positive ions on the wave. And you might say that average translational kinetic energy or average kinetic energy for the ions is greater compared to that of free electrons simply because of their heavier masses. Electrons are very lighter, though they are moving very fast, even then their mass is very small and average energy is going to be greater for positive ions only. Despite all that, when they collide, the energy is transferred by the free electrons to the positive ions. Now, suppose this is one positive ion, another positive ion, electron collided, and you see electrons will go on colliding because positive ions are not mobile, they are fixed, they are bound. Only free electrons are available for free motion all around in random or zigzag manner. Electron collides this way, uncertain. In any direction, these electrons may move and will collide. So, suppose we apply the electric field. You have applied the electric field, this side is positive, this side is negative. Electric field has been produced this way, in this direction. Since electrons are negative, they will always experience a force opposite to this field. That means electron will always have the acceleration in this direction, as I am showing over here on the board. Electrons will have a particular force in particular direction, and because of that we could say that the velocity they will gain before the collision with the other positive ion, that could be written as Vu plus A T. They will start with zero velocity after the collision, and acceleration is going to be F upon m. What is t? Time between two collisions, that's known as relaxation time. This is of the order of 10 to the power minus 14 second. It's represented by the letter tau that I have written over here. Force is E upon m tau. This is V. So, you could write the velocity before the collision is going to be E upon m into tau. If we consider the average for all the electrons, we'll find one particular velocity equal to this value that will be known as drift velocity. Drift velocity is always opposite to the electric field, but it is always along the field, opposite and along the field. See, electrons are moving very fast with thermal velocity 10 to the power 6, whereas this drift velocity is going to be very small, of the order of this thing 10 to the power minus 4 meter per second. The two things must be clarified by an example. I'll illustrate right now. You see, just imagine a very classical, typical Indian family having 10 members, mother, father, and kids. The youngest person in the family is 6 years old and is very naughty in nature. They are on the expedition of morning walk and have to cover 1 kilometer distance, means final destination is at 1 kilometer. But this youngest person, what he does, this naughty boy, he goes on running throughout the motion. He goes on, he turns back, takes toffee, takes chocolate, shares chocolate, and all that he goes on doing, and he is running very fast. But when all the members reach over the destination, he too reaches at the same time. That means although he was running very fast, but in that particular direction, he is also having the same velocity as all the family members. This is exactly the case over here, that electrons have been running very fast in random direction, in different direction, but in one particular direction they are having very small velocity. That's what we call drift velocity. You see, for the thermal velocity, we follow the same relation as that for RMS velocity of gas molecules, which is given by this formula, Vrms root 3 kT upon m. Here m is mass of electron and k is Boltzmann constant, T absolute temperature. So obvious, by increasing temperature, RMS velocity or the thermal velocity will increase, and relaxation time is given by mean free path over RMS velocity. Its order is 10 to the power minus 14 second, and this free path distance between two collisions, it's about 10 to the power minus 8 meter. The two are related with each other. So, we have covered how these are related with each other. Here, one thing you must remember, that number of atoms per unit volume, N0 we have used, and electron density N. N0 can never be greater than N, means number of free electrons per unit volume for monovalent is going to be this. This is electron density, number of free electron per unit volume. this is number of atoms per unit volume. If it is divalent, then you will have 2 and 0, because every atom is going to contribute to 2 free electrons.